Hello everyone, this is Dr. Webb. Welcome to the second video for Math 430 Abstract Algebra. In this video, we are going to be defining groups. Then we're going to look at some examples of some common groups that we'll see a lot. And we're also going to be proving some basic properties that all groups have. So let's jump right into the definition of groups. Okay, so we're going to have G be a set, and star here be an operator on G. And so operator just means that it takes two things from G together and spits out something else. We're going to say that G is a group under this operator if all of the following properties are satisfied. So first of all, the operator has to be closed on G. And so that means that A star B is going to be inside of G for all A and B in G. The operator needs to be associative. And so the way to think about associativity is if you're going to do the operation twice, it doesn't matter how you arrange the order, right? So if I'm going to do A star B star C, I can do A star B and then star C, or I can do A starred to B star C. So it's kind of like you're doing B star C first, and then you're doing A star on that. So neither of these ways of doing it is going to change the ultimate output. Our set needs to have an identity element, and so an identity element, if you apply it with the operator to anything else in the set, you get that thing back again. So for any A star E is equal to E star A is equal to A. And lastly, everything in G, every A in G, there needs to be an inverse element. So we're going to call it A inverse, such that A star A inverse gives you back the identity, and also A inverse star A gives you back the identity. So here's some examples of some common groups. Most of these you're familiar with or have seen at least once. So the integers, that's that Blackboard Z. The rational numbers, that's the Blackboard Q. And the real numbers, that's that Blackboard R. Those are all groups under addition. So for closure, that's just saying that x plus y is in whichever one of these we're talking about. If x and y are in whatever one of these we're talking about, associative, so that's saying if I do x plus y plus z, I can do x plus y and then add c to that, and I'm going to get the same thing as if I do x plus the quantity y plus z. So our identity, well, if I do x plus 0, same thing as 0 plus x, that's always going to return me back x for either integers, rational numbers, or real numbers. And last but not least, our inverses. Well, what am I going to add to x to get 0? I'm just going to add minus x. And so that works for all three of these groups with addition. Okay, now if I take the rational numbers and the real numbers and I remove 0, these are both going to be groups. But that doesn't work if I take 0 away from the integers. That's not going to be a group. So let's think about, at least let's start with the rational numbers and the real numbers. So same as before, closure, x times y is in the rationals or the reals, so long as both of them individually are. Associative, same as before. If I do x times y times z, multiply x times y first and then multiply z, that's the same thing as doing x times yz. What's the identity for these? Well, the identity for both of these is 1, right? If I do x times 1, that's the same thing as 1 times x. That's just going to be back x. And lastly, what are inverses for non-zero rationals or non-zero real numbers with multiplication? Well, I'm going to multiply x by 1 over x. That's going to give me back 1. Right. So why does this work for the rationals and the reals but not the integers? Well, for the integers, this is not possible. The inverse is not possible multiplicatively if x is not equal to plus or minus 1, because 1 over x is not going to be an integer. And so that's why the integers fail there. It has the other 3 properties, but not the last one. Okay, so this is something we saw in the first video, right at the very end. If I take some n greater than 2 and I look at that set of the integers modulo n, that is going to be a group under addition. It's going to be very similar to the rules for addition we saw for the integers and the rational numbers and real numbers. So I'm not going to go through all the properties there. If I already have some group with operator star, then I can make matrices where the n by m matrices, where the entries are in G, and that's going to be a group under matrix quote-unquote addition, where what we mean by addition is if you add 2 matrices together, you do the operator entry-wise. So top left entry to both of them. If you're adding it together, you do the operator on the 2 entries. And so, typically we think about this, say matrices on, say, real numbers, then, our operator here would still just be addition. Matrix multiplication, that's going to be a bit more complicated. In general, there's going to be all sorts of issues with that. But at times, matrix multiplication can give you a group if you restrict your matrices suitably. Lastly, one that we looked at together is we saw an example of what's called a dihedral group, and so that's D sub n, where D sub n represents the set of symmetries of a regular n-gon. So we looked at symmetries of a square. This is always going to form a group, where the operation for this is composition. So by composition, talking about do one symmetry, do one transformation, and then another one. That's going to give you another symmetry, another transformation. Okay, so let's talk about some basic properties of groups. So first one, in any group, the identity element is unique. There can only be one identity element for the group. So why is that true? So let's assume that E1 and E2 are both identity elements in G. Okay, so then what we're going to do is let's look at E1 applied to E2. So E1 star E2. Now, on the one hand, E1 is an identity element, and so if I apply it to E2, that's not going to change E2. And so that's going to equal E2, and this is coming from the fact that E1 is an identity element. On the other hand, since E2 is an identity element, and I apply it to E1, that's not going to change E1. So E1 so this overall is going to be equal to E1. And so this is because E2 is an identity element. And then looking at this, we have E1 is equal to E2. So if they are both identity elements, they had to have been the same thing all along. Okay, secondly, in every group, we have both right cancellation and left cancellation. So right cancellation and left cancellation laws hold. So what does that mean? By right cancellation, we mean that if we have B star A is equal to C star A, well, then we can cancel off the A's and we can be sure that B is equal to C. Left cancellation is similar, except everything happens on the left. So if I have R star S is equal to R star T, then S has to equal T. We can cancel off the R's on the left there. Okay. So why is this true? So let's focus on right cancellation. The proof for left cancellation is essentially the same thing. So we're doing for right cancellation. Okay, so suppose we have B star A is equal to C star A. Well, we already know that G is a group, so in particular, A has an inverse element. And so when I can apply that inverse element to the right side on both of these. So I can do A star A and then apply A inverse, and that's going to give me the same thing as C star A, and then apply A inverse. Okay. And so this is coming from the fact that B star A is equal to C star A. Now, since this is a group, star is associative, so I can rearrange how I'm thinking about these. And so in particular on both sides, I can put parentheses just on the A star A inverse. And then by the definition of these being inverses, both of these are equal to the identity. And so we have that B times the identity is equal to C times the identity, and B times the identity, that's B, C times the identity is C, so B equals C, and we're done. Left cancellation is the exact same thing, except then we'd multiply, if we're looking from up there, we'd multiply R inverse to the left on both sides, and that would cancel off the R. So we're always able to cancel off elements on both sides of an equation. That's always nice to do. Means algebra is sort of fitting in with the algebra that we know. Okay, so if you look back at the definition for groups, you notice that we said it has an inverse, and we said automatically that it is both what's called a left inverse and a right inverse, that we can cancel it off on the left and the right, it doesn't matter. And so you might say, well, does that mean that is that a special property to assume that left inverses are right inverses? And the answer really is no. They're sort of forced to be. Once you have left inverses and right inverses, they're forced to be the same as each other. So what do I mean by that? So we're going to prove this in a little bit more general setting than groups. We're going to say let S be a set, and star is a closed and associative operator on S. And suppose that S has an identity element. Then if we have anything in S that has both a left inverse, so if I take A as an S, I'm going to call the left inverse A sub L to the minus 1. And so that means that if I multiply A, if I do A sub L minus 1 star A, that's going to give me E. So that's what makes it a left inverse. If I apply it to the left of A, it cancels it off. Also, if it has a right inverse, so AR sub minus 1, so then if I do A star A sub R minus 1 and get back E, well, the only possibility is that those two are equal. Okay. So if you notice, this is slightly weaker than saying that S is a group. I'm just saying that for any element that has both left inverses and right inverses, then they have to be, those left and right inverses have to be equally to each other. So this would apply to something like S could be a set like matrices with multiplication here. This theorem applies to that too, even though that's not necessarily a group. Okay, so why is this true? Well, on the one hand, what we're going to look at is I'm going to start with A. On the left, I'm going to multiply by its left inverse. And on the right, I'm going to multiply by its right inverse. I'm going to look at this element right here inside of S. Okay. So on the one hand, if I group those two together, I'm going to get, by associativity, I'm going to get the same thing as I would get if I grouped the other two together. And so this is by associativity. Well, on the left-hand side here, we have that A sub L to the minus 1 star A, that's the identity. So that's E star A sub R minus 1. On the right-hand side, I'm going to use the other property of the right inverse. So that's going to give me E. And so then, since E is the identity, I have A sub R to the minus 1 is equal to A sub L to the minus 1. And we're done. Right? So once we're in the group, if you find the left inverse for an element, then that also has to be the right inverse for the element. But that also means that anytime you're dealing with matrices, matrix multiplication on n by n matrices, if you can find a left inverse for the matrix, then that is also automatically a right inverse for the matrix. Okay, so let's talk about some broad different types of groups. So if a group has only finitely many elements, there's only finitely many things in the set, then we're going to be really creative and call it a finite group. On the other hand, if it has more than finitely many elements, so it has infinitely many elements, like the integers or the rational numbers or real numbers, then we're going to call it an infinite group. For any group, if the operator is commutative on that group, so that means that A star B is equal to B star A for any A and B and G, then we're going to say that G is an abelian group. So I'm capitalizing abelian because it's named after Abel, who was a mathematician about 200 or so years ago. I think he was the first one really to focus in on studying these groups with commutative operators, and so we call those groups abelian after him. And in this case, rather than saying star to signify that we're using an abelian group, we're going to usually use addition if we're talking in general about an abelian group, because we're used to addition always being commutative. If you think about it, you can't think of any place where addition is not commutative. So what if the operator is not commutative? And so that just means, what does it mean for it to be not commutative? That doesn't mean that the operator is never commutative. It just means that there's at least some example of elements A and B and G such that A star B is not equal to B star G. Then in that case, we're going to be really creative and call it non-abelian. And so if we're talking about groups in general from here on out, and we don't know whether it's abelian or non-abelian, we're just going to assume, to make full generality, we're just going to assume that it's non-abelian. And instead of this star that we've been using in this video, we're just going to use multiplication. So either a dot for multiplication or just two elements next to each other to represent that. So we're just going to think of the operator as being multiplication. And that just sort of fits into, if you think about multiplication on different types of sets as an operator, sometimes it's abelian, like with the integers or rational numbers or real numbers, and sometimes it's not, like with matrices. And so that idea of multiplication sort of fits into this generality. Okay, so for any group, in particular finite groups, so groups that have only finitely many elements, we're often going to look at what's called the Cayley table for the group. And so what the Cayley table is it's a table that lists out all the possible ways to apply the operators to two elements. So you can kind of think about this as being sort of the multiplication table. For the group. So Cayley was was a British mathematician, and so it's named after him. I think he's more recent. I think he's more like maybe 150 years ago. We looked together at the symmetries of square before, D4, dihedral group on a square. And so we started working on this. And so this is the Cayley table for that. So where the R's are our rotations and the S here are the different flips that we saw. Okay, and so in here, in the way that set this up, the top row, this is the element that we're applying first. So this is the first element. The first column, this is representing the second element. And so if I do something like I pick, say, this spot right here, well, this is underneath R180 and in the same row as F1. And so this is saying that if I do R180, then flip over a line of slope 1, that this is the same thing as doing a flip over the line -1. And so that's how we read this. And so oftentimes, especially in these next couple weeks, we're going to be making Cayley tables for groups, because this table right here holds an awful lot of information about the group. And we will be looking at that and learning how to parse that information out of it. Okay, the last thing I want to talk about is this little theorem, is if you have two elements applied to each other, then you have, you want to find the inverse of A times B. Well, that inverse of the quantity A times B is going to be A inverse times B inverse times A inverse. Okay, and so if you notice, the order inside the parentheses, once I apply the inverse, it gets swapped. So as AB inside the parentheses, once we apply the inverse, it swaps the order there. It gives us B inverse times A inverse. And so oftentimes, this is sort of in a tongue-in-cheek way called the socks and shoes principle, right? So if you're going to wear socks and shoes, how do you put them on? Well, you would put your socks on first and then your shoes on after that, right? Well, so what's the inverse of that? Well, that would be taking both of them off. So how do you, when you're wearing socks and shoes, how do you take those off? Well, the first thing you do is you would take the shoes off, and then you would take off the socks, right? So you can kind of think about, in this case, A you can think about as being putting on socks. B would correspond to putting on shoes. So if I put on socks and shoes, the inverse of that is taking off shoes, then taking off socks. And so in fact, putting on socks and shoes, this is often used as an example of a non-commutative operator on yourself. Putting on socks and then shoes is not equivalent to putting on shoes and then socks. Okay, so why is this true? And this really is just a simple calculation. If I look at AB times B inverse A inverse, well, I can order this any way I want. And so I can do the B times B inverse in the middle first. And so that's going to be A times the identity times A inverse. But the identity is not changing anything. And so that's just going to give me A times A inverse. And they cancel each other off and give me just the identity. So this tells me that AB times B inverse A inverse is the identity. And then since we saw that we have this right inverse, then it's also the left inverse. And so the inverse for AB has to be B inverse A inverse, because it canceled it off on one side. That is all for this video. I will see you again soon.